Welcome. This is the regression analysis course. I am Nicoletta Serban, Associate Professor in the School of Industrial and System Engineering. The topic covered is simple linear regression, and we're moved from estimation to statistical inference. In this lesson, we'll learn about statistical properties of the estimated coefficients, and we'll learn how to use the statistical properties in making inferences such as confidence intervals and hypothesis testing. We'll begin with deriving the statistical properties of the estimator for beta 1. For example, the expectation of beta 1 hat is equal to beta 1, the true parameter. And the variance of this coefficient of this estimator is sigma square of SSX. And I'll show you a brief derivation of the expectation of beta 1 hat, and you can use the same sequence of derivations for the variance of beta 1 hat. So let's go back to the formula of the estimator for beta 1. We can rewrite that as the sum of a constant times the random variable yi, where that constant is ci, is denoted here by ci. So what that means is that beta 1 hat is a linear combination of random variables, and we know from basic statistics that the expectation of a linear combination of random variables is equal to the linear combination of the expectations. So now we replace the expectation of the random variable of the response variable yi with the linear relationship in x. We divide that into two sums, and now the first sum is equal to 0 because the sum of the constants is equal to 0, and the sum of the constants times xi is equal to 1. So what we get is that the expectation of the estimator for the slope parameter is exactly beta 1. This property, the fact that the expectation of the estimator is exactly the true parameter that we're estimating, is called unbiasedness. What that means is that beta 1 hat is an unbiased estimator for beta 1, and that's a very important statistical property of an estimator. Let's dive more into the properties of this estimator. I will remind you that the beta 1 hat is a linear combination of the yi's, the response variables. Under the normality assumption, the beta 1 hat is thus a linear combination of normally distributed random variables, and thus beta 1 hat is also normally distributed. So along with the expectation of variance from previous slide, with the property that beta 1 is normally distributed, now we get the distribution for beta 1 hat. However, the sampling distribution of beta 1 hat is not useful because sigma square is unknown. So what we'll need to do in order to get a full specification of this distribution is to replace sigma square with an estimator, and we can use the estimator we discussed in the previous lesson, which is the mean square error, or the sum of square residuals divided by n-2. Now, because this estimator has a chi-square distribution with n-2 degrees of freedom, now we get that the sampling distribution of beta 1 hat is a t-distribution with n-2 degrees of freedom. The n-2 degrees of freedom come from the fact that the distribution of the variance, of the estimator variance, is a chi-square distribution with n-2 degrees of freedom. And we're going to use this distribution, the sampling distribution, to derive confidence intervals and also to perform hypothesis testing procedures with respect to beta 1. So this is the confidence interval for beta 1, and this is based on the assumption that we have normality, the deviances are normally distributed, or the y's are normally distributed. So let's look a little bit of this confidence interval. Again, the sampling distribution of the estimator beta 1 hat is a t-distribution, and if we want to obtain a 1 minus alpha confidence interval, then we can center the confidence interval at the estimated value for beta 1 plus or minus the critical point t, which comes from the fact that the sampling distribution is a t-distribution, and we carry over the degrees of freedom n-2. Alpha over 2 comes from the fact that we want a 1 minus alpha confidence interval, and we multiply this critical point with the standard deviation of beta 1. Again, the t critical point comes from the sampling distribution of beta 1 hat, and the standard deviation of beta 1 hat comes from the variance of beta 1 hat, which I shared with you in one of the previous slides, but replacing sigma square with the estimator, the mean square error. If we want to perform hypothesis testing on beta 1, for example, we may want to test whether beta 1 is equal to 0 versus the alternative that beta 1 is not equal to 0. The procedure is going to be very similar to testing for the mean parameter in a standard normal distribution problem. The t-value now, that is the difference between the data and the null hypothesis. That is, here is the estimated value for beta 1 minus the null value, in this case is 0, divided by the standard error of the estimator. That's going to be the value of the t-value. And if that t-value is large, we reject the null hypothesis that beta 1 is equal to 0. And if the null hypothesis is rejected, we interpret this that beta 1 is statistically significant. You will see that in this course, I will use this terminology across many contexts. Statistical significance means that beta 1 is statistically different from 0. But what if we want to change the procedure and we want to test whether beta 1 is equal to a constant versus beta 1 not equal to that constant, where that constant can be 0 but can be a different value as well? Remember, this is the t-value. We can replace 0 with c, depending on the constant and null value in the null hypothesis. When we reject this is when a t-value is large, when a t-value is larger than this critical point in absolute value. The absolute value of the t-value is larger than this critical point. We can also make this decision based on a p-value, which is going to be the sum of the tails on the left and on the right of the t-value. If the p-value is small, for example, it's more than 0.01, we would reject the null hypothesis. What if we will change the procedure and we're interested in testing whether the regression coefficient is positive or negative? That means we'll change the alternative hypothesis from beta 1 different from 0. Now we're interested whether beta 1 is greater than 0 or beta 1 smaller than 0. In this case, the p-value will change in the sense that we're interested on only one of the tail. For beta 1 greater than 0, we're interested on the right tail. For beta 1 smaller than 0, we're interested on the left tail. The inference for the intercept parameter is going to be similar to the inference for the slope parameter. Beta 0 hat, it's also a linear combination of random variables, a linear combination of y's. We can derive similarly that the expectation of this estimator is equal to the true parameter. Thus, beta 0 hat, it's an unbiased estimator of beta 0, and the variance of this estimator is on the slide. With this information, and with the fact that beta 0 hat is the linear combination of normally distributed, we can have the sampling distribution is also a t-distribution. Thus, the confidence intervals is going to be very similar to the confidence interval for beta 1 hat. It's centered at the estimator beta 0 plus or minus the critical point from the t-distribution times the standard error. To summarize, in this lesson, we learned about statistical properties of the estimated coefficients, the intercept and slope, along with estimation of confidence intervals and hypothesis testing, and some statistical inference for the regression coefficients. Thank you.